And let me see here. And just want to announce everything is taking place here at this hotel. So all size event also will be here. No in Nash, just because here also we have internet access, so all the facility that people need for the side event, they can actually, I don't know, go Zoom and everything like that. So don't go over Inach. Well, it's my pleasure to present you Laura DeSantis, Geology and Geophysics from the National Institute of Oceanography and Applied Geophysics from Italy. Please welcome.
Maybe I need this. Is this working now? Yes. Okay, good. Oh, that's me. Okay, let's start. Well, first of all, of course, let me thank Jorge and all the organization for this ISIS. Also for inviting me here. It's a real pleasure for me. That's my first time in Punta Arenas. You can believe it, and it's really nice. I'm so happy to be here to share this with you and discuss all possibility for future cooperation. Really stimulating, really exciting. When I was asked to give this keynote, I was thinking about the title, the topic, and I thought, well, for a geologist talking to a group of geologists, it may be quite easy to talk about the importance of geological boundary conditions to understand the Antarctic ice sheet. So I said, okay, let's go for 2. Oh, much better. Sorry. My voice is low, I'm sorry, but that's how I am. Okay, so because I'm also very much convinced about the importance of geological boundary conditions. So yeah, that's basically what I'm going to focus on my talk. If we look at the ice mass balance, we do see that it's not uniform. We have seen this picture many times already. And we do see that there are some regions where it's changing fast. But what's the reason for this? Well, in order to know what's going on, we need to know more about Antarctica. And not just about the climate distribution, it's also about the geology, the bedrock, what's below the Antarctic ice sheet. If we compare, for example, the distribution of subglacial lakes and the basal meltwater rate, it seems that it's pretty much localized, where we do have the highest ice mass balance lost. And that might be dealing with different in the lithosphere as well, because we do see that this particular region is also where the lithosphere is thinner. And so there might be something related with the heat flow that probably is triggering more subglacial meltwater. But we do also see that this region is where the ice sheet is marine-based. So the elevation of the bedrock is very deep. I mean, it's the base of the ice is very deep below the sea level. And therefore, it might be that this ice sheet is particularly vulnerable. It's thinning fast because of the ocean warming, because this is also where the ocean is warmest along the West Antarctic margin. That's where the ocean is warmest and is approaching the continental margin. and it's entering actually the continental shelf and reach the grounding zone. So there might be a connection between all of these processes and observations, but maybe the picture is more complicated than what we think, because if you can see, there is some other sectors of Antarctica which are also where the ice sheet is marine-based, but they are not losing mass so fast. And the ocean is not so cold there, and the continental shelf is not cold. It's still a cold, what's called cold cavity. So maybe this is something going on here. There is a delay in how the ice sheet is responding to the climate, or maybe it's just a different boundary condition, or maybe the interplay of them. There is something we still don't know much. And if we do see, for example, the Ross Sea and the Weddell Sea, they also have a kind of intermediate behavior, because they are part of the West Antarctic ice sheet, which is marine-based, so it's supposed to be vulnerable, but the cavity, the continental shelf, is cold, although the ocean is warm near the continental margin. So maybe one of the things that we can do as a geological community is to try to disentangle all of this information and try to check if there is any correlation between climate and geology, and look at the past, reconstruct how this specific region changed through time, and how the interplay of climate and geology modulated the way how the ice sheet responded to past global changes. So the rest of my talk will be about the Ross Sea, because that's where I've been working more during most of my career, but it's also where there is a huge amount of data that were collected so far. And so we have been able to reconstruct the geological evolution of this region of Antarctica reasonably well, and it could be used to think about how climate and geological boundary condition modulate the interaction between ice sheet and the ocean. It's not over, huh? Okay, first of all, let me thank the IODP Expedition Science 374 Science Party and Shore-Based Party, which is much, much larger. This was an incredible expedition that we carry on in 2018, and with Rob Mackay, who is the co-chief, and from University of Victoria in New Zealand, and Denise Hulainek, who is a staff scientist now in Germany, and a really nice team. And some of the shore-based are actually here, Natalia and Varela from Chile, and Luca Zurli and others, lots of early career scientists, lots of PhD students, still working on this data set, which is an incredible data set. So how the Ross Sea look like today? I put these nice cartoons because I think they are very useful, very clear, explain how the situation of Ross Sea is today in terms of distribution of water masses. If you see, the Ross Sea today is characterized by high salinity shelf water, which is a very salty and very cold water masses, -2, which is forming in the Western Ross Sea, mainly in the Polynya, due to the action of katabatic winds that freeze the upper fresh layer of the sea and create the Antarctic surface water, which is fresher and cold than the high salinity shelf water. And the high salinity shelf water is a dense water, which is filling the deepest cavity of the Ross Sea. This transect here is going along here across the Ross Sea shelf. And it shows that the bathymetry in this position here is quite deep. So because it's a dense water, it's filling the deepest basin, and it's flowing south and also north, and then it spill out the continental margin and flow westward. The rest of the Ross Sea is shallower. The bathymetry below the Ross Ice Shelf is shallower, and it's filled with ice shelf water, which is much less salty than the high salinity shelf water, because it's forming due to the melting of the Ross Ice Shelf. So it's much fresher, but still very cold. And then the modified circumpolar deep water, which is a core of warm water, which is coming from the ocean and is entering the continental shelf from this particular corner here, mainly, and reach the Ross Ice Shelf and melt the Ross Ice Shelf from underneath, but it doesn't reach really from the model that Tinto et al. 2019 made. It doesn't reach the inner part of the Ross embayment because the cavity gets much, much narrower, and so there is no space for modified circumpolar deep water to intrude southward, and so it's basically, that's why it's basically still a kind of cold cavity. What's nice is that what Tinto show is that there is also a boundary between the western embayment and the eastern Ross Sea embayment. It's not only in terms of water masses and cavity size. The western is a bigger cavity, the eastern is a smaller cavity, but it's also in terms of tectonics, because the western embayment is basically as a tectonic lithospheric character, more similar to East Antarctica, and the western embayment is what's related to Western Antarctica. And this is also a boundary between a very elevated topographic bathymetric region to the west, with banks which are horst, formed during the West Antarctic Rift System. And to the west, there is a much flatter and more depressed area, which was also formed during the West Antarctic Rift System, but it's much, much younger and so less elevated. And this is also a boundary between the different situation for the last glacial maximum that was mapped by Protro et al. That shows that the West Antarctic, the Eastern Ross Sea, belonging to the West Antarctic realm, is more like where the ice sheet was reaching out the continental shelf edge, while in the Western Ross Sea, which is more elevated, but it's where the ice sheet was pinned and there were calving bays, so the ice sheet wasn't reaching the continental shelf edge in the Pennell trough and in the Joides trough. So there are quite different regime in the Ross Sea in terms of climate, water masses distribution, bathymetry, and also the geological control for the bedrock. And that was the motivation why we put our drill sites in this particular corner, because we wanted to check if there is any sign in the geological record of these changes, how the boundary condition changes through times in this corner, how the modified circumpolar deep water, which is entering the continental shelf right here, what's the history of this current in the past, and what was the relationship with the ice sheet. In 2017, we visited this corner with the OGS Explorer in the frame of Eurofleet's project and Plenaría projects. And we actually confirmed that this region is characterized by dense cold water, which are exiting the continental shelf and speeding up along the flank of the Eastland Bank and cascading downward. And then circumpolar deep water, which is rising up, is upwelling on the southeast side, and it's replacing this dense water in the continental shelf. The multi-beam shows that the margin is actually incised by galleys, And these gullies have different characters, but they're basically formed during past ice sheet advance, which was carving the continental shelf and incising the glacial valleys. And there is a population of gullies also in the buried sediment. So that means that this region recorded also previous ice sheet advance and retreat. So it's particularly suitable for checking what happened to the ice sheet comparing to the exchange of heat between ocean and Antarctic waters in the past. But, where the current is particularly strong, there is not much sediment because it's been kept by the current. So what we did, first of all, was to check where to drill in order to get the more expanded section, because we need a continuous record for our geological reconstruction. So we found 2 spots to the right and to the left of this very high-speed along-slope current. So on top of the bank, on the edge of this bank, the Isling Bank, and down to the levee of the Hillary Canyon. So we basically were aiming to drill through this very nice sediment drift, which has this typical sigmoidal shape with the reflectors pinching toward the edge of the drift, where the current is so strong that prevents the deposition of the sediment. But we drilled where we guessed that the current was generally slower. And for this reason, we have a thickest accumulation of sediment. We were away from the grounding zone, because the grounding zone is a place where the ice sheet is advancing, retreating, and basically eroding. So we didn't want to have a record full of hiatus. And so we drilled right in front of the grounding zone, but in a shallower place, shallow enough to have enough foraminifera for our dating and biogenic component, and to get the most proximal record and also the paleoceanographic record of both the cold cascading rocky bottom water and the warm uprising modified circumpolar deep water. In the continental slope, at the base of the slope, on the flank of the levee, we drilled the 1524 here, in this corner here, because that was the site that was detecting the overspill of turbidity current, cascading current, driven by rocky bottom water, which was forming in the continental shelf, spilling out the canyon head and flowing downwards. So in order for you to understand the different character of the records that we will be looking at, I just put this cartoon here showing how is the distribution of the sedimentary phases. So the green are those forming in a glacial ice proximal environment near the grounding zone, below the grounding zone, or near the grounding zone. The muddy, the gray, is where the sediments form below the ice shelf in a kind of distal environment with not much biogenic component, because below the ice shelf there is no light and there are not so many nutrients. So that's the typical phases. The diatom and the mud rich in biogenic material and ice raft debris is the one that we find in an open water where we do have sea ice sometimes, or a kind of polynya environment. And then at the edge of the continental shelf, we have a residual material, which is formed by, it's particularly coarse because it's swept by the current. So this is site 1523. Again, it's here at the edge of the bank, over here. And what we see is that it is formed by an alternation of open water to ice distal, sometimes ice proximal sediments. And from the age model, we were able to actually correlate our record with the Andril sediment core, which is located in the southwestern corner of the Ross Sea. And so we made a connection between the, the continental shelf edge and the inner, what it could be a paleo ice cavity below the Ross Ice Shelf. And then we were also able to correlate with the ocean, the deep water record at 1525 and 1524. And what's so nicely from our reconstruction is that during super interglacial of Pliocene and Pleistocene, we do have evidence of incursion of circumpolar deep water. This was a time when the climate was warming everywhere in the world. We do have 4 to 5 centigrade more than today. Our record shows that we have much less sea ice, much less bottom water formation, much weaker current, because we do have foraminifera, which are typical of subtropical and temperate region, and we also have a gap in turbidity record in the deeper water. We have a lot of diatoms on top of the mound, so this was a particularly warm time, which was recorded basically everywhere in the Ross Sea. And so we show that that suggests a real polar amplification during this time. This is supported by the seismic, which shows also that during this time, basically the pink unit here is a unit which is draping the mound, which are rowing both in the deep water and also on top of the bank during the Miocene. But during the Pliocene, the pink unit, everything stopped. It was a time when nothing happened, just hemipelagic draping. And so the conceptual model that we came up with is that basically the regime of the current was slowing down between 5 and 2.5 million years. And the circumpolar deep water was able to enter the continental shelf because the easterlies were much weaker and shift over the continental shelf. And then in the Pleistocene, the current got stronger again, and the ice sheet was again approaching the continental shelf, delivering sediments in the deep water, and the mound started to grow again. So in the Pleistocene, we have a much drier and colder climate, and we do see this also from our course. So the foraminifera now, they are much different. We have typical forms of shelf break and upper slope stronger bottom currents. They're also suggesting more corrosive water, so more Antarctic bottom water production, more polynya. So this was a time of gradual cooling, which was recorded by our core. We do also have the mid-Pleistocene transition suggesting a long warm interval in our core with no turbidites. So basically, to sum up this part of the talk, what we got from looking at the margin of the Ross Sea, we do see that there is evidence of polar amplification of climate, with the geological boundary condition basically driving the incursion of modified circumpolar deep water from the ocean to the shelf margin down to the Ross Ice Shelf cavity during the warm Pliocene. And so the morphology, basically the change of the landscape in the continental slope, conditioned the incursion of this modified circumpolar deep water along this corridor, which was the paleo panel trough, the canyon, the Hillary Canyon, the panel trough, and the Glomar Challenger down to the Ross Ice Shelf. And the way that the circumpolar deep water intrude and has prolonged stability inside the Ross Ice Shelf was favored by the landward deepening continental shelf that was achieved by this time. But how about the past condition during the Miocene and the Oligocene, when the continental shelf was not so large, like in the Pliocene, was up to this position, so much smaller continental shelf, much shallower, and was also less mature. The margin was less mature, so it was not long after the rift, so it was still the thermal subsidence, the thermal tectonic subsidence was still quite high, so it was influencing a lot the way how the accommodation space for the sediments were provided and the platform for the ice sheet actually to ground. We have an extensive seismic data coverage, and that allows us to actually reconstruct the paleobathymetry that tell us that in the old time, the continental shelf of the Ross Sea was quite different. It was characterized by islands, subaerial islands, as shown by this drill site here. And these islands were above sea level, and that's where the ice sheet started to develop first, and then expanded seaward down to the present day. And that was the time when that was the evidence for Wilson et al. To infer that the West Antarctic ice sheet was much broader already in the early Oligocene, but it was mainly a terrestrial ice sheet, so contributing much more to the global sea level change. During the early Miocene, between the early and late Miocene, the ice sheet was fluctuating, was growing, because the climate was cooling, gradually cooling. The CO2 dropped, but the climate was also fluctuating between warm and cold, and so the ice sheet was advancing and retreating and building up its own platform, but eroding the interior and broadening the continental shelf. So during the early Miocene, the Ross Sea was still much narrower, as I say, and most of the western Ross Sea was very shallow, subaerial. And we drilled this site here at the mouth of the Panel Trough to check how the ice sheet, even at that time, reacted to climate change and how the landscape actually was driven the ice sheet advance and retreat. And what we found is that there was indeed enough accommodation space for the ice sheet to advance across this bank, shallow bank, create a sort of grounding zone, similar to what we've seen already, from south to north, that we drilled here at 1521. And at this time, the rate of subsidence was very, very high, and it was probably during one of the cold orbits when the ice sheet was growing on the western Antarctic ice sheet, mainly, because the tectonic subsidence was slowing down, as suggested also in the Western Ross Sea. We have a major hiatus in Andril here, and we have coastal glaciers advancing, and we have a fall of static sea level of up to 60 meters. So that was a time when the ice sheet was growing, and particularly the West Antarctic ice sheet, because Jim and Luca, they did find clear evidence in these sediments here of the fingerprint of West Antarctic ice sheet from strontium and neodymium isotopes, much different from what before and what's after that. This situation is different in other sites. This is our site, 1521, in the middle. And the SCP-273 to the right is here in the Gioides. The Gioides was already subglacial and ice proximal. But in the Eastern Ross Sea, the SCP-272 shows that during this time, there was a large embayment still open to the ocean, no ice sheet, but ice distal record with diatoms. So in this case, again, the landscape actually regulate the way how the ice sheet was spreading over the shallow banks and not reaching out the ocean yet. Later on, the ice sheet retreated, and then advance again, even during the Miocene climatic optimum. That's surprising, because it should be warm, the ice should be gone, but that's not the case. The ice sheet was actually over this site once again. This time was from East Antarctica, that's about based on the provenance, and it's consistent with what we see in the seismic, which shows it's showing basically a grounding zone from coming from the Transantarctic mountains, carving this little basin and reaching out our edge. During this time, the sediment rate is still high. We do have evidence of, from the palynology of brackish water, fresh water. So it was a terrestrial ice. And there are lots of benthing forams, very well preserved, so not much rocky bottom water was forming at that time, so no polynya. Incursion of warmer water from plankton foraminifera. So also in the Miocene climatic optimum, we do have evidence of polar amplification. And in the end, the very, very warm Miocene climatic optimum, we do see the disappearance of the ice sheet. So no ice sheet anymore. We have mollusk, intact valve, so very, very slow motion at the seafloor. Maximum both east and west Antarctic ice sheet retreat, no much clast, rare forams, and incursion of modified circumpolar deep water, once again, across the Paleo-Hillary Canyon, across this corridor down to the Panel Trough. And then in the late Miocene, cooling, the ice sheet was overreading this region, grounding everywhere, eroding the bedrock and creating this very nice glacial erosional feature. So that's almost the end. I don't know, am I late? Or I didn't watch the watch. Okay, I'm going faster now, almost there. That's the end of the story. So in the late Miocene, the ice sheet is growing again, but this time all of this region is eroded. There is not much space anymore for the ice sheet to deliver sediment. There is not much space for the sediment to fill the basins. There are no basins anymore. Everything is filled up. But there is enough room at the margin in this region here, at the continental shelf. And so the ice sheet is building up this green wedge here during the late Miocene, which the shape is much different, and it depends on the landscape. It depends on the geological boundary condition, because where there is no space, like along profile 1, we do have progradation. There is no space in the continental shelf to actually build up any sediment. But where there is space, like along profile 3 and 4, we do have progradation, but also aggradation, because there is space. So it depends. When we look at the region, we try to reconstruct the history of a region. It's not enough to look at one single core, one single seismic profile. You need to have a map. You need to have an idea about the landscape and the change of this landscape through time. So what's happening in the late Miocene is that we had delivery of sediment from both the Marie Byrd land, the West Antarctic ice sheet, the East Antarctic ice sheet, basically from everywhere. But the main thing is that major glacial trough, north-south trending, formed in the Eastern Ross Sea. That's the first time. The first time that we do have evidence on seismic as well of the source from the West Antarctic ice sheet, the real source from West Antarctic ice sheet, which is also recorded at this site. But this is going to be too long for you to show what's happening here, and there are some more work needs to be done, so maybe next time I'll show you something about this site as well. But there is a story here about the change of the East Antarctica versus West Antarctica. But what we see is that during this time we have accumulation of sediment at the front of this margin, which is basically this green prograding margin. And after that, the continental shelf became over-deepened everywhere, not only in the Western Ross Sea, but also in the Eastern Ross Sea. And so there was not much time anywhere for sediments to aggregate. Everything was prograding everywhere. And only at the very latest time, after 2.5 million years, we do see a sort of aggradation and a real change, a tilt in the, from seaward deepening to landward deepening. So that was the time when the ice sheet became really, it was slowing down, was responding to the climatic cooling in a sort of slow down motion because the continental shelf was huge, was very much extended, landward deepening, and once the CDW was able to enter the continental shelf across this weak zone, the Hillary Canyon corridor into the panel, triggering basically the ice sheet to retreat, filling the basin inside because the continental shelf was landward deepened. Only at that time the ice sheet was able to retreat. And then it took time for the ice sheet to build up again. So that's one of my final slides, showing basically that what we do see after our reconstruction in the Ross Sea is that gradually the bedrock were deepening, and it drove the transition of terrestrial ice sheet to marine-based ice sheet since the early Miocene down up to the modern time. So the subglacial topography evolution basically increased the ice sheet sensitivity to ocean warming. So if we look at where we are now, we are approaching a much warmer climate with very high CO2 concentration. And if we go back to mid-Pliocene or even to the Miocene, we are not going to have this kind of scenario anymore. So the bedrock will be very much different, would be like this. So it would be even a more vulnerable scenario. So what we learned from the Ross Sea paleoclimatic and paleoceanographic record, we do learn that boundary conditions are important. That was obvious at the beginning, but I hope I demonstrated once more that that's it. And climatic boundary condition, of course, we need them. We need the ice to the climate to force the ice sheet to advance and retreat, and to have we do see polar amplification at the high latitude, but we do see that geological boundary conditions actually were driven the ice sheet advance and retreat. The roughness of the bedrock, the extension of the continental shelf are really fundamental, because climate alone is not enough to force ice sheet changes. We really need to do such kind of studies also in other regions of Antarctica, and I know there is a quite extensive work in the Amundsen Sea already, but there is a very special corner which I'm also very fond of, which is Wilkes subglacial basin. We don't know much about this. It's also another key area that we, as a community, we should investigate a bit more, because it's vulnerable. It's not reacting so much yet, apparently, but it's probably close to cross a threshold. And we need to know more about the geological boundary condition to understand how far are we from such a threshold, and how fast then the ice sheet retreat when we cross it. So yeah, I leave it there. Thank you. No time for questions.
All right. Thank you. We have time for 2-3 questions.
2-3
comments. Please, somebody.
I'll be here until Friday, so if you are shy now, you can talk.
You've shown some paleobathymetry maps. I was wondering whether those were compensated for the compaction, isostasy, and subsidence.
Yes, we did some work. It's not published yet. We still have to do something on this side. Yes, we did some backstripping on 2D sections in the past, and that's published. But we use the map to do the 3D backstripping now. I'm still waiting for some paleobathymetric constraint from the drill sites, because we need them to actually tie our models. But yes, we are working on this right now.
Thank you.
Thank you very much for your presentation. You mentioned the contribution of the biological boundaries as well. How relevant are those in the present structure of the information that is presented?
Biological
boundaries, yes, because there are biological systems existing there. So I'm asking you, how relevant is the contribution?
Yeah, the biology is fundamental. Of course, we need to know more about the paleobiology, actually, how for example, how the carbonatic fauna was distributed in a different time when, the compensation depth was likely very much different. So we have a quite large team of biostratigrapher working on this issue, using foraminifera and diatoms together with other proxies. So we try to understand, for example, how fresh and how corrosive the water were, and to compare with the foraminifera existing at that time and today, and see what's the frame, the water depth and the temperature and salinity frame that help us to actually calibrate the paleoproxy with the present day. So it's an issue, but there is a SCAR action group actually focused on calibrating proxy and paleoproxy, and Joan Etourneau, who is probably is there. Joan, can you say hello? Okay. If you want to talk to him, Joan is leading this action group at SCAR, and is combining biological and geological expertise to find out how can we use the paleoproxy based on the present day distribution.
Okay, and the last one, please, go ahead.
Thanks for this very interesting talk. I'm very intrigued by your mentioning of the workspace area for the next focus. You mentioned that it requires a more extensive and multidisciplinary research over there. I wonder what's your thought about what exact data you will be looking for to help solve those problems. Are you looking for more drilling, seismic studies?
Everything. Well, as you see, this region is pretty much unknown. I mean, the continental margin is huge. There is a huge low-bed shape continental margin, and there are some sediment cores, very few, that tells that once upon a time, this margin was very much dynamic. It was delivering sediment because the continental margin built up. But now it's stable. Apparently nothing is happening there, and so we need to figure when was the time when the ice sheet was dynamically responding, was advancing and retreating. So we do need drilling, but for drilling we do need seismic, and we do need multi-beam. But we also need to know what the present day situation is, because nowadays there is a perennial sea ice covering the continental shelf. That's the reason why we don't have bathymetric data. So we need to know what's the role of the sea ice now there to actually dam and protect the ice shelf to calve and collapse. And maybe in the past the sea ice was not there. Maybe in a warmer condition the situation was different. So the ice shelf, the circumpolar deep water reached the continental shelf, melt the ice shelf, And maybe this model that was compiled by Rob De Conto with the dramatic retreat in the weakest glacial basin, maybe it's real. So yes, we need everything. But there is already a large community working on this. We have a proposal and submitted to the European community, and Linda is also going to the region. Linda Arbrecht with the Australian vessel is going there in January. And we have a Polarin cruise scheduled in 2027. So the community start to be more and more interested in the region, but there is room for everybody. So of course, go for it.
Okay, we thanks once again, Laura, please. Well, and now it's my pleasure to announce Marcelo Lepe, paleontologist and paleobotanist from the University Mayor of Chile, former director of INACH, and one of the vice president of SCAR. Please welcome Marcelo. The floor is yours.
Can you hear me now? Yeah, perfect. I will try to do my best to fit to the time, but was actually a perfect introduction to my theme. It's the idea is to present you the new brackets that we are trying to put to one iconic genus of plants that are living today in the southern hemisphere, but it has a very long record in the natural history of Gondwana, starting around 80 to 90 million years. Some authors promote the age more than 90 million years ago, but as far as we know, with the fossil record, but especially with the macrofossils, now we are trying to put in a better way in the complete sequence of the evolution of the southern continents. So I belong to the University Mayor. It's a GEMA Center, has one interesting group of scientists devoted to Antarctica, but also part of the Millennium Nucleus, one project that is studying the early evolution of mammals in South America, but especially in Chile. But I want to start always, this is my, a kind of memory about Erebus and terror. The best photos that I have obtained are from a movie, actually a TV series, The Terror. Probably you have seen it. Because this was the expedition of James Clark Ross. And one interesting thing, the scene of the time. Oh, sorry. What's this one? Okay. Sir Joseph Dalton Hooker was on board. He has a perfect opportunity that Charles Darwin never had to visit Antarctica, to trying to connect the findings of some very interesting fossils in Antarctica with the findings that he had in South America and also in Oceania. That's the movie. If you want to check it, it's max today in Latin America. I don't know around the world, but you have to check it. It's very good. Remember that these two vessels, after ending the campaign in Antarctica with James Clark Ross, started the very famous and sadly ended expedition of Franklin to try to find the passage to connect the both oceans through the Arctic, but the vessels finally disappeared, and that's all. I don't want to make a spoiler about the movie. But also, there are some very interesting features. It's working? Yeah. There are very interesting features related with the biogeography of especially plants. Those are the biomes of the world. And if you look carefully, there's a green color, especially in the center part of Chile until the southern tip, this is Cape Horn. Part of them are also in the other side of the Andes in Argentina. But this color is only present in the other side of the world. It's in Australia, Queensland, and especially Tasmania. I don't know why New Zealand is not here, Gary. I don't know what happened. Sorry. It's not my problem. Dalton Hooker has the opportunity to visit both continents, and he immediately saw there was something interesting about the environment, the landscape that he had the opportunity to collect plants, animals, but immediately he had created a concept, the Antarctic flora. But this Antarctic flora wasn't in Antarctica. He was very creative. And you can imagine that was more than 100 years before the tectonics, plate tectonics, and Alfred Wegener's ideas. So how this guy imagined that animals and plants were connected through Antarctica, connecting distant regions as Oceania and South America. So he has this idea of the emerged lands. So the idea of having lands connecting the regions was immediately proposed, but after some letters with the Geological Society, he have received bullying from the scientific community, and after 100 years, again, when the plate tectonics appeared, and everyone says, okay, Dalton Hooker was really wrong. But we have to look carefully. Sir Joseph Dalton Hooker is not Doctor Strange, please. Benedict Cumberbatch in the movie Creation. I am a very good fan of movies, as you can see. In a very good characterization. And the interesting thing was the letters that Dalton Hooker sent to Darwin, discussing some early ideas about the idea of evolution. So after some years, this senior researcher Arnold Edward Ortman in 1902 also have a hypothesized, it's a very hard word for Spanish speakers, it's a hypothesized the existence of land bridges connecting different and distant regions because there are evidences in different continents about this. And also the green bird experience, I tried to make it many times, but no good ideas came to my brain. But for Edward Suez, apparently, the legend says that was the first concept of having all the continents joined in one point and having this exchange of fauna and flora. Sorry. But also, one interesting concept that is also connected with the problem, especially for Southern and North America at the end of the Cretaceous, glacioeustasy. Glacioeustasy means when we have a rapid fall of temperature, the recruitment of ice in the continental shelves promotes a very fast, in geological terms, of a fall of the sea level. So this is interesting because when you have platforms around the continents, of course, this can modify extremely the shape of one continent and connecting these joint areas of the world. So this started to be evident in the work of Christian Lienert, one very surprising paper. I put all the photos of Lienert in only one sequence. It was quick, so I would put it again. Pay attention, it's Jurassic, Beressian, Aptian, Mid-Cretaceous, Upper Cretaceous, and the interior sea of North America have disappeared. Why? The explanation of Lienert is, again, a big fall in the global temperatures in the surface of the oceans and also in the deep waters, in the mid-Campanian, and then repeatedly in the Maastrichtian. At least 4 events in this early work. After this, become more than 20 different sources of information about what happened at the end of the Cretaceous. But something really interesting happened in an extreme greenhouse world at the end of Cretaceous with more than probably 1,000 ppm of CO2. And these cooling events recorded in not so high latitudes started to be a question. What happened in high latitudes? So the first works came from the Arctic, but also increasing the resolution of the different models. As you can see here, Miller has a very not detailed curve of evolution of the sea level. Hack in 2014, another one, and then this superposition of points that are showing that probably with better resolution, there are more factors affecting the sea level more than the tectonics, more than also climate change. All of this just to reach this point. This is one map produced by Marwick in 2004. I'm still having this map. One of the best is showing the Austral Basin or Magallanes Basin, the James Ross Basin, and the small area that was really close to Antarctica and probably affected, very affected by the sea level because there were shallow waters in the area. And this huge and provocative idea promoted by Zinsmeister in '79, the Wedelian province. The Wedelian biogeographic province originally was created for the animals, marine animals from coastal zones, intertidal and no more than 10 meters depth. But during the time that was expanded, today the terrestrial realm is also considered part of the Wedelian biogeographic province. But we have some interesting questions, and was part of the last Cretaceous Symposium in Vienna. Why we have to think that if we have the oldest record of so many plants and animals here, have to take this route to Oceania and not the other one. Interesting, because the circumantarctic current, the pattern of winds, when you have species that are completely dependent of the wind for the pollination and for the dispersion, probably the more realistic movement could be move around this. Of course, not in a flat world. And new pieces of evidence came later. One Chilean colleague, Rodrigo Otero, started to work with the plesiosaurs, mosasaurs, and pliosaurs from Gondwana. And he found a very interesting pattern that was connecting directly New Zealand, part of Australia with the southern basin especially Magallanes Basin, but also in the Chilean coast and in the Proto-Atlantic area of Argentina. So why Nothofagus is considered key in terms of the explanation about biogeography? One first thought is, well, the earliest South American record was documented by Per Dusen, that was in the Swedish expedition that was also here in Magallanes region, have visited Torres del Paine, have visited one locality that I will mention later, that is Cerro Guido. Also, Srivastava defined Nothofagiditis phytogeographic province in terms of the distribution of pollen. But I am really careful, take care about the record of pollen. There was a big discussion. Mary Detman says usually when you don't have more than the 10% of representation of Nothofagus is not autochthonous origin. Probably the source could be 1,000 kilometers. And we have demonstrated that, and probably some other programs do it, in Antarctica, having traps of pollen. You can capture pollen from Tasmania in the peninsula. We have a very good record from 2007, 2009, and with several different types of pollen from anemochotic plants and anemophilic plants. So one better approach is leaves of plants. It's not easy to move the plants to other place. Could be transported, yes, but destroyed also. They are very delicate. So when you have a very good deposit of leaves, you have also the opportunity to have an approach to an autochthonous locality. The other authors reported the Paleocene leaves with a possible Notophagasia affinities from Kazakhstan. The genus is Ushia. We were recently comparing using a new tool of artificial intelligence, and the interesting thing is not very close to Nothofagus. So here there is a question that I want to make at the end, but why the name Nothofagus was created in the early 18th century, 1830, but the name means false beach, in reference to the Fagus genus of the Northern Hemisphere. So until today, we have in our mind the idea of the origin in the Northern Hemisphere or in this group, ancestral group of plants, but the fossil records is saying another very controversial thing. The oldest records of all the order Fagales is today in Nothofagus. So we have to change the books. This is something really interesting. The low abundance of pollen and absence of macrofossils of Nothofagus during the early Eocene warm phase suggests that the genus was confined to high latitude and high altitude refugia. Never have to forget there are stratification. If you visit the Chilean forest, especially for whom was in Pucón the last Open Science Conference, there are levels, there are strata of Nothofagus from the valley up to the mountains, and this is a repeated pattern exactly in the way that Humboldt has this very famous certification, the Chimborazo in Ecuador. And these lines are dynamic. When you have the ice, the permanent ice moving up with the climate change, is also happening with the bands of plants are moving up, some of them, other ones disappear. So it is when you have the discussion about the distribution of this kind of plants, you have to have in mind a 3D model. but I want to put it in a better way. We are in a casino, so I imagine that we have a poker. So the first ace is anemophily. So the pollen of Nothofagus is dispersed only by wind. Only by wind. No animals, no other vector than wind could disperse the pollen of Nothofagus. The second one is anemochory. So Propagus are also dispersed by wind in a short distance. Third, the seeds have a very low dispersal ability. They can fly, it depends of course, of the species, but the longest distance are around 15 kilometers that have been demonstrated. This is the longest way to distribute in between islands. But longer distances, for example, in Chile, we have many continental islands with all the elements of the Chilean forest, but without Nothofagus. The permanent winds came from the sea to the interior, so the way back is impossible. Germination is, viability is very short in time, and seeds are intolerant to the seawater. This is key. They're starting a lot of experiments around the world trying to demonstrate this, and finally agreed that the salty water, of course, is an enemy of the seeds of Nothofagus. And currently has a disjoint distribution, but a very good fossil record. This is something really interesting and useful when you're trying to compare the distribution of this kind of plants from the Gondwana in Antarctica. The previous discussion, I don't want to mention the name of this Dr. Cornelius Fanstenis, that's all, have proposed that the center of origin and diversification was New Caledonia, because there is one group of the 4 subgenera of Nothofagus that is exclusively from this area. But Robert Hill and Mary Detman, unfortunately, I don't have a photo of Mary Detman. I was looking for a photo for many years, but I have only the Robert Hill. But they have proposed, well, they have proposed a magic area in between the northern tip of the peninsula and the southern tip of Patagonia, an area of origin, the center of origin and diversification. And that was only with a few elements. This is extremely interesting because in the 96, there was no record of Nothofagus valid with a stratigraphy and good dating in Antarctica. So to having, just as a final review, the 4 subgenera of Nothofagus today are subgenus Nothofagus, that is only present in South America, all are in Chile, are the group of Nothofagus adapted to the cold conditions, probably one of the last groups living Antarctica, but also adapted to the hardest conditions they are living here in Magallanes, but also in the high Cordillera. The second group is Fuscospora, a very interesting group, old one, with Nothofagus guni in Tasmania, and another 3, one that define the group is Fusca, Nothofagus fusca from New Zealand, and the only living relative in South America is Nothofagus alessandri. Unfortunately, it's a tree that is in great risk in Chile at the moment because of the big fires have disappeared almost the 40% of the population, and the breeding trees are still in one area that is in great risk every year. But alessandri is probably one of the grandpas of the rest of the Nothofagus of Gondwana. The other old group is Nothofagus, subgenus Lophosonia, sorry, with 4 representatives in the Chilean-Argentinian forest, and also Menciesi, Kuningami, and Murray in Australia and New Zealand. And finally, Brazospora, as I mentioned, Phansthenis, have populated because it has the longest diversity of Nothofagus, but all are confined to this area. Here, one of the happiest moments in my life after the birth of my kids. That was in Nelson Island some years ago, and we have discovered in the intertidal area, as you can see there, is the water. In the afternoons, the water came and covered all our site, so we had to come back every morning and clean it again. The other interesting thing was only 20 minutes from our Escudero station, so having the good tide, you can do it and go back for a dinner in Escudero. It's very comfortable. But the rocks here were finally very interesting. That's the locality, as I mentioned, Fildes Peninsula, Escudero Bay Station, Frey Station there, the Chinese and the Uruguayan, the Russian, all the family here, and this point that is Ree Point in Nelson Island. This is a very small area uncovered by ice. And we found this. It's a fantastic, very good preservation, leaves. Was a litter, actually, a lot of leaves. We have more than 200 in probably 4 more morphotypes. We are publishing soon 2 of them, new species, and the first for the companion. In age, as you can see, they have between 80 and 83 million years. So it's the oldest record of leaves of Nothofagus in the world. So it's the first bracket of my talk. So other photos, we have corroborate this with the work of palynology. In our team, usually we work together, geologists, palynologists, paleobotanists, but also paleozoologists. The idea is to have an approach from different sites, and this is very characteristic. Nothofagus has a very special features in the pollen grains, so was also in the same levels. And as you can see here, there are big leaves, really big leaves. It's coincident with the time. Companion was extremely hot, and we know that Nothofagus could adapt to these tropical to subtropical conditions. In the same project, we moved to Patagonia, Torres del Paine area, for the group that is moving on Saturday to Torres del Paine, probably. This is one area that is very remote. Actually, from the last civilized point, you have to walk 4 hours to reach the camp. And this is the excavation in one of the sites of a big valley. This is the area where the mammals, dinosaurs, but also close to here, Nothofagus, have appeared. But it's also a delta, a deltaic system that have been controlled by the tidal elements and especially by the sea level, having the alternance of marine and continental sequences. Extremely interesting when you have the end of the Cretaceous dominated by this level, the sea level rise and fall. But also, in terms of the word of Stephen Jay Gould, this is a kind of piston, an engine for evolution. When you have connection and disconnection constantly through 20 million years, you have the opportunity to have the apparition of particular and singular shapes and then connected again, and all the elements of the modern ecology become important. When in this area, we found originally 4 levels of Nothofagus. Finally, we have 8. Some of the leaves are perfect, has all the features, including the patterns of venation, and also are under the way of publication today. This is my dry hand in the field, but very beautiful material. This is the oldest locality of Nothofagus in South America, and the differences are 83 to 78. Really close, only 2 degrees of difference in between the other locality in Antarctica. But it's very interesting to have this difference. We have started to test if we have more localities closer to the 80 million years, but actually we don't have any evidence having also the record of plants in older sequences in the same area. Oh, it's in Spanish, sorry. So is that the origin of the South American forests? It's a very good question. Why? When we started to compare the rest of the flora that was together with Nothofagus, there was Araucaria. Yeah, okay, Araucaria, but Araucaria sectio eutacta. The section eutacta is today living only in Oceania. So only in Australia, New Zealand, and Norfolk Islands. It's not related to the Columbia section that has these 2 species of Araucaria from Chile and Argentina, and also Brazil, the Plan Alto. So we can say, Australian. The second one is Retrophyllum. Retrophyllum is closely related to the carp, but it's also present in the northern, living today in Colombia and Venezuela, but also in Australia. Brachychaeton is a bottle tree from Australia. It's endemic from Australia today. And this is the oldest record in the world of Brachychaeton. Schizia aculia, ferns that are also connected with the story. Eucalyptus, probably, it's a typical from Australia, but also the oldest record in South America. Papua cedrus, cedrus from Papua, also with Australian relations. And Nothofagus, as I mentioned, all are closely connected with a group that today have 3 living species in New Zealand and Australia, and only 1 in South America. So if we compare the distribution of these plants, the oldest record of many plants that are living today in Australia and New Zealand has their origin in South America. It's very controversial, yes. We have to discuss it, yes, a lot. But the good thing about fossils, you can change it. You can transform it. It's a very hard piece of evidence. And talking about the other bracket, we have recently sent, and this is the preprint of the youngest Nothofagus in Western Antarctica. Probably you have seen or remember the work of a Sirius group, Bidmore Glacier in East Antarctica, in the Transantarctic Mountains. This is one piece of evidence from the early Miocene in Kinjor Island. Also, a very interesting piece of evidence. Have all the features of Nothofagus, a very right secondary vein, a straight primary vein. No, a lot of characteristics, but is coincident with the periglacial environment that probably has, but also is closely resembles the Nothofagus that are living in this condition in the Andes and also in areas as Patagonia. Summarizing, I don't know, how is my time? A few minutes? Yeah, okay. I will pass it quickly. We have the oldest record of notophagus then in Rip Point, as you can see there in Kinjor Island, 83 to 80 million years ago. There's no other record of this age around the world. So it is extremely interesting if they are related with the groups of Northern Hemisphere. We have seriously to discuss new ways to come into Southern Hemisphere because the old models are not fitting very well with this age. Las Chinas Valley, then the second oldest record in South America. Also, we have 20 million years of record in Las Chinas Valley, but start to appear more frequently also in Antarctica, in Admiralty Bay. Yeah, we are in the KPG boundary. Also, with some discussion, Anna Moser from Poland have changed some ages, but I'm still confident about one or two of these levels that are probably Cretaceous. Then in South America started to appear more to the north. It's Cerro Funes, Palacio de los Loros in Argentina, and still in Admiralty Bay. Estancia Colón in Coloncura in Neuquén in Argentina. We are in 50 million years, early Eocene. So start to appear a lot of records in Patagonia and in the extreme south, also in Tierra del Fuego. And then the oldest record the youngest record in the last one in Antarctica, in Western Antarctica is, first Fossil Hill in the Eocene. In New South Wales in Oceania, in Bugileo and Loreto Formation in 35 million years ago. Farellones, Rio Guillermo, Loreto, and Sierra Baguales in Patagonia, early Oligocene. They has starting the biggest expansion of notophagus around the world. Late Oligocene, also in New Zealand, in Australia, in Tasmania, and also Chile and Argentina. Early Miocene, the biggest extension. This is the widest distribution of notophagus ever. Many localities. I'm sorry, I passed. And the last apparition of notophagus in Antarctica and West Antarctica was Cape Melville. So continues their conquer of New Zealand, Australia, especially Queensland, Tasmania, and South America. But here we have something controversial. It is the age, more connected with your talk, in Bidmore Glacier, but there are a big range of interpretations about the age of this youngest notophagus in Antarctica, the last one disappearing in Bidmore Glacier, that some authors says 5.3, other ones 9.2, other ones 14. So it is a lot of controversy about the age of this locality. Anyway, it's the youngest notophagus, the last one leaving Antarctica, and then the historic distribution of notophagus in Antarctica ended at this moment. Another interesting thing, one of our colleagues, Leslie Manriquez from geology, have worked in the project since the very beginning, and we have detected a new KPG boundary inside a interesting deposit of coal. So it's a continental deposit in high latitudes. There are only 2 around the world. In southern hemisphere and high latitudes, the rest of the deposits are with marine influence, shallow marine, deep marine, but marine anyway. And also some other controversial plants start to appear. This Cunoniacea, typically from Australia, Ceratopetalum has a fossil record that is ranging the 80 million years, also here in Patagonia. So also will be the oldest record of the plant. And probably last week, you have seen some news about this mouse-like new mammal discovered together with the Notophagus and other plants in the Las Chinas Valley in Torres del Paine. The third mammal, and also is a famous locality of this dinosaur. Here you have the backbone, ribs, head. So this is the early preparation. Finally, we have one of the most complete dinosaurs in South America. It's a small one, ankylosaur, but with a very special tail. Was a front cover of Nature, the only one in our life probably. But very interesting because it's closely related with something that is key. The southern tip of South America was isolated, become the expression of many animals and plants and various particular singular shapes. Some of them are more related with Australia and Antarctica than the rest of South America. And this is one. Finishing, don't worry. Cumbarasaurus is from Australia. It's closely related with Stegosaurus, that is our ankylosaur with this particular tail. And Antarctopelta is from Antarctica, is the most related ankylosaur in the world. The tail. And this is my dream. Finally, one paper have produced a toy. So I'm really happy about this, especially my kids are really happy. I am really proud that they say now, after years, that is important. So thank you very much.
Oh, thank you, Marcelo. Just for, we know that we are just coffee time, but we can have 2 questions, short answer for Marcelo. Or you are very happy, very hungry, actually.
Or sleepy.
Sure.
Just a quick question about the Notophagus at the SDP-274 in the Ross Sea. Is it reworked, I guess?
Sorry?
It's reworked. It's
no, the discussion is about the dating, because originally were dated with diatoms that is supposed that were deposited with a marine spray over the fossils. The construction of the community are showing that it's not reworked because it has
but at the site, the SDP-274 is in the deep ocean. It's located in the ocean. It's
yes, in a marine, in a front marine, yeah.
So now, I mean, it's being transported and deposited there.
Yeah, but they have leaves. So the important thing about the leaves is cannot be transported for a long distance. The source have to be close, but also other elements as huncus. It's a complete community. It's not only Notophagus. I'm talking about the key genera, but there are other groups, animals and plants, insects. It's a very interesting community. So the dating of this locality passed over 20 years. of discussion. Interesting.
Thank you. One more. Okay. Over there. Okay, last one.
Hi, Marcelo. What about the Notophagus record from Seymour Island, from La Meseta Formation?
From?
La Meseta Formation.
Yeah, Paleocene, yes. Wasn't there because something really weird happened in that site. But yes, La Meseta has a very interesting record, but it's starting in Sobral. But my attention was in Vega Island, especially because there are some reports of these very strange lobed forms of Notophagus that are closely related with the eastern flank of the isthmus connecting South America and Antarctica, are not present in the other side, and probably are related with a phenomena that is microclimatic. The winds, the western winds, and the transportation of water over the mountains have produced probably this effect, but that are only at the moment present in the eastern side and in Patagonia.
Thank you.
Okay, we thank once again Marcelo for his great presentation. Just one announce for those that are interested in the side events, rings will be here at 5:30 to, I don't know, 7:30. So please go to and have your coffee, tea, or whatever.